Positioning of the H0 tap on the back of a delta-wye transformer, especially those with larger kilovolt-ampere ratings, is not unusual. The primary reasons for this placement relate to minimizing interference with the other taps and enhancing accessibility for maintenance and testing procedures. The H0 tap frequently serves as the main connection point for the transformer. Locating it on the rear facilitates simpler access to the primary connections, avoiding the need to maneuver around other taps. Moreover, positioning the H0 tap on the back can contribute to lowering the potential for unintended disconnection or harm to the primary connections, while the majority of other taps are situated on the front of the transformer to ensure straightforward access during operation. The H0 tap typically requires access only during the initial installation or subsequent maintenance activities. This reduced need for frequent access diminishes the importance of having it in an easily accessible location. In essence, the placement of the H0 tap on the back of a delta-wye transformer is a design consideration that balances operational convenience for the other taps with safety and accessibility for the primary connection point, especially for higher kilovolt-ampere rated units where space and safety are paramount. The taps on a transformer allow for adjustments to the voltage ratio, compensating for variations in the supply voltage and ensuring the secondary voltage remains within the desired range. The location of these taps is carefully considered to facilitate both operation and maintenance. The H0 tap, being the neutral point on the high voltage side of a delta-wye transformer, is crucial for establishing a stable ground reference. Its placement often reflects a compromise between ease of access and the need to minimize potential interference with other components. The design and layout of transformers are governed by various standards and best practices, aiming to ensure safety, reliability, and ease of maintenance. Manufacturers like MGM adhere to these guidelines while also incorporating their own design considerations to optimize the performance and usability of their products. The location of the H0 tap is one such design consideration that can vary depending on the specific transformer model and application. Understanding the rationale behind the placement of different components on a transformer is essential for electrical engineers and technicians involved in installation, maintenance, and troubleshooting. Factors such as safety, accessibility, and minimizing interference all play a role in these design decisions. The H0 tap provides a grounded reference point for the primary winding. This grounding is critical for safety and proper operation of the transformer and connected equipment. Placing it on the back reduces accidental contact during normal operation. The configuration of delta-wye transformers is such that the delta-connected primary winding provides a path for third harmonic currents, which can be problematic in Y-Y transformers. The Y-connected secondary winding provides a neutral point, which is often grounded to provide a stable reference for the load. The H0 tap is connected to this neutral point. Proper grounding is essential for preventing voltage imbalances and ensuring the safety of personnel and equipment. The location of the H0 tap is influenced by the physical layout of the transformer windings and core. Manufacturers strive to optimize the design to minimize size and weight while maintaining performance and safety. The positioning of the H0 tap is also influenced by the need to provide adequate insulation and clearances between the high voltage primary winding and other components. Transformers are designed to operate within specific temperature limits. The location of the H0 tap and other components can affect the temperature distribution within the transformer. Manufacturers use thermal modeling and testing to ensure that the transformer operates within safe temperature limits. The H0 tap location can also be influenced by the type of cooling used in the transformer. For example, oil-filled transformers require space for the oil to circulate and cool the windings. The location of the H0 tap must not impede the flow of oil. Maintenance procedures for transformers typically involve inspecting the taps and connections for signs of corrosion or damage. The location of the H0 tap should allow for easy access for these inspections. Testing of transformers may involve measuring the voltage and current at the H0 tap. The location of the H0 tap should facilitate these measurements. The H0 tap is typically made of a high conductivity material such as copper or aluminum. The size and shape of the tap are designed to minimize resistance and ensure a reliable connection. The H0 tap is typically connected to a grounding electrode conductor, which provides a path for fault currents to flow to ground. The size of the grounding electrode conductor is determined by the size of the transformer and the grounding system. The grounding system must be designed to meet the requirements of the National Electrical Code, NEC, and other applicable standards. The H0 tap is an essential component of a delta-wye transformer, and its location is carefully considered by the manufacturer to optimize performance, safety, and ease of maintenance. The design and construction of transformers are complex processes that involve a wide range of engineering disciplines. Electrical engineers, mechanical engineers, and materials scientists all contribute to the design and manufacture of transformers. The H0 tap provides a crucial grounding point that enhances the safety and stability of the electrical system. Its strategic placement is a testament to the thoughtful engineering that goes into transformer design. Different transformer types, such as step-up and step-down transformers, serve distinct purposes in electrical power systems. Step-up transformers increase voltage levels for efficient long-distance transmission, while step-down transformers reduce voltage levels for safe distribution to homes and businesses. The H0 tap plays a vital role in both types of transformers, ensuring proper grounding and system stability. The materials used in transformer construction, including the core, windings, and insulation, are carefully selected to withstand the high voltages and currents involved. The H0 tap is typically made of a durable, corrosion-resistant material to ensure a reliable connection over the transformer's lifespan. Transformer testing is a rigorous process that verifies the transformer's performance and safety. Tests include insulation resistance tests, turns ratio tests, and impedance tests. The H0 tap is often used as a reference point during these tests to ensure accurate measurements. Transformer maintenance is essential for prolonging the life of the transformer and preventing failures. Regular inspections, cleaning, and tightening of connections can help identify and address potential problems before they lead to costly repairs or downtime. The H0 tap should be inspected regularly for signs of corrosion or damage. Transformer protection devices, such as fuses and circuit breakers, are used to protect the transformer from overloads and short circuits. These devices are coordinated to trip and isolate the transformer in the event of a fault, preventing damage to the transformer and connected equipment. The H0 tap is connected to the grounding system, which provides a path for fault currents to flow to ground, tripping the protection devices and clearing the fault. Transformers are used in a wide variety of applications, from small electronic devices to large power grids. The size and type of transformer used depends on the specific application and the voltage and current requirements. The H0 tap is a common feature in many types of transformers, providing a crucial grounding point for safety and stability. The efficiency of a transformer is a measure of how much of the input power is delivered to the output. Transformers are typically very efficient, with efficiencies ranging from 95% to 99%. The efficiency of a transformer is affected by factors such as the core material, the winding resistance, and the load current. The location of the H0 tap does not directly affect the efficiency of the transformer, but it can affect the temperature distribution within the transformer, which can indirectly affect the efficiency. The impedance of a transformer is a measure of its opposition to the flow of alternating current. The impedance of a transformer is important for determining the fault current that will flow in the event of a short circuit. The location of the H0 tap does not directly affect the impedance of the transformer, but it can affect the grounding impedance, which can affect the fault current. The National Electrical Code, NEC, provides requirements for the installation and grounding of transformers. These requirements are designed to ensure the safety of personnel and equipment. The NEC specifies the size of the grounding electrode conductor that must be connected to the H0 tap. The NEC also specifies the requirements for grounding the transformer enclosure. The location of the H0 tap is an important consideration in the design and installation of transformers. By understanding the function and location of the H0 tap, electrical engineers and technicians can ensure the safe and reliable operation of transformers. The kVA rating of a transformer indicates its apparent power capacity, which is the product of voltage and current. Selecting the appropriate kVA rating for a given application is crucial to avoid overloading the transformer and causing damage. The H0 tap plays a role in ensuring that the transformer operates within its rated kVA capacity by providing a stable grounding point. The turns ratio of a transformer is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. The turns ratio determines the voltage transformation ratio of the transformer. The H0 tap is connected to the neutral point of the Y-connected secondary winding, which is essential for establishing the correct voltage transformation ratio. The insulation of a transformer is critical for preventing short circuits and ensuring safe operation. The insulation materials used in transformers are designed to withstand high voltages and temperatures. The location of the H0 tap is carefully considered to maintain adequate insulation clearances between the high voltage primary winding and other components. The core of a transformer is made of a magnetic material such as laminated steel, which provides a path for the magnetic flux. The core is designed to minimize losses due to hysteresis and eddy currents. The location of the H0 tap does not directly affect the core losses, but it can affect the overall performance of the transformer. The windings of a transformer are made of copper or aluminum wire, which carries the current. The windings are insulated from each other and from the core. The location of the H0 tap is connected to the neutral point of the secondary winding. The cooling of a transformer is essential for preventing overheating and extending its lifespan. Transformers are cooled by various methods, such as air cooling, oil cooling, and water cooling. The location of the H0 tap must not impede the flow of cooling fluid or air. The noise level of a transformer is an important consideration in some applications. Transformers can generate noise due to vibrations in the core and windings. The location of the H0 tap does not directly affect the noise level of the transformer, but it can affect the overall vibration characteristics of the transformer. The size and weight of a transformer are important considerations in many applications. Transformers can range in size from small units used in electronic devices to large units used in power grids. The location of the H0 tap can affect the overall size and weight of the transformer. The environmental conditions in which a transformer operates can affect its performance and lifespan. Transformers are designed to withstand a wide range of environmental conditions such as temperature, humidity, and altitude. The location of the H0 tap does not directly affect the environmental performance of the transformer, but it must be protected from corrosion and other environmental hazards. The life expectancy of a transformer is typically 20 to 30 years. The life expectancy of a transformer can be extended by proper maintenance and operation. The location of the H0 tap does not directly affect the life expectancy of the transformer, but it must be inspected regularly for signs of corrosion or damage. The cost of a transformer is an important consideration in any application. The cost of a transformer depends on its size, type, and features. The location of the H0 tap can affect the cost of the transformer, as it can influence the complexity of the design and manufacturing process. The selection of a transformer is a complex process that involves considering a wide range of factors. By understanding the function and location of the H0 tap, electrical engineers and technicians can make informed decisions about transformer selection and application. The standards for transformers are developed by organizations such as the Institute of Electrical and Electronics Engineers (IEEE) and the International Electrotechnical Commission (IEC). These standards specify the requirements for the design, construction, testing, and performance of transformers. The location of the H0 tap must comply with these standards. The location of the H0 tap is also influenced by safety considerations. The H0 tap must be located in a safe and accessible location, and it must be protected from accidental contact. The location of the H0 tap is an important consideration in the design and installation of transformers. By understanding the function and location of the H0 tap, electrical engineers and technicians can ensure the safe and reliable operation of transformers. The H0 tap serves as the reference point for the grounding system, ensuring that fault currents are safely directed to ground, protecting personnel and equipment. Its careful placement reflects a commitment to safety and reliability in electrical power systems.